Okay, we are going to talk about impedance. This is the combined effect of all the resistances and the reactance in the circuit. Formally, it is defined as the ratio of the amplitude of the source voltage to the amplitude of the source current. So if we have a circuit like this, as I told you, impedance will be the combined effect of the resistance and the reactance of the elements in the circuit. As I told you, if we have a source voltage like V, let me make it S. Let's say this is the amplitude of the source voltage, and it is driving a source current with the amplitude IS. Then we define impedance, which is the letter Z is used for impedance. Then we can have Vs divided by Is. Remember, the subscript there indicates denotes the source, and the capital letters indicate the amplitude. We often use small letters for the sinusoidal wave, and then the big V to represent the amplitude. So this is the actual definition of impedance. At any point, if we find the ratio of the source voltage, the amplitude of the source voltage to the amplitude of the source current, then it gives us the impedance of the circuit element. We can also calculate impedance using this formula. We've already established that the reactance of the capacitor, which is Xc, is given by 1 over angular frequency multiplied by the capacitance. And the reactance of the inductor, or inductive reactance, is given by the product of the angular frequency and the inductance. So if we have all these values, and we have the value of the resistance, then the impedance, simply the square root of just look at this expression. So the square root of everything here. Remember, the two reactants are opposing each other. So one subtracts from the other. Either you make it XL minus XC, or XC minus XL. It gives you the same thing. But remember, the square here will nullify any negative effect that come out from this difference. Okay, so if you are able to compute this, you add it to the resistance here, then you can find the square root that will give you the impedance. There is this other factor about impedance. We should have used the phasor diagram to explain the relationship between phase difference between the voltage and the current. We can also find the phase difference between the current and the impedance. The impedance is also a phasor. It's rotating, so it's a phasor. I think if there need be, I may have to give you a new video on phasor diagrams, but let's not worry ourselves so much. It will be equal to tan inverse. I think we should find it here. So tan inverse of XL minus XC. Yeah. The negative angle has little effect on tan, so XL minus XC over R, if you find the tan inverse, to give you a certain angle. The impedance is the combined effect of all the resistances in the circuit and the reactances in the circuit. So we find it by either the ratio of the source voltage amplitude to the source current amplitude, or we can also find it by finding the square root of this whole sum. So we realize that the reactance of the capacitor, or the inductive reactance, they depend on the frequency of the system. This frequency is the frequency of the source. Please, we have another frequency I'm going to point out too. So let's not confuse it with that. This angular frequency here is the frequency of the source itself. the source is pushing the current back and forth with a certain number of cycles per second. And that's the angular frequency we are talking about. So this frequency here is the frequency of the source. If I don't give any subscript here, then it's the frequency of the source. Alright, so we are going to try to plot a graph of how the reactances behave with frequency. Let's start with that of the resistor. The resistance does not depend on frequency. So if we have here to be the angular frequency, then the resistance will remain resistant throughout every frequency. If the frequency is 50 Hz, 60 Hz, or whatever, remember this one is equal to 2 pi f. So it's in radians per second, but we can also talk about it as the frequency in hertz. So this can be in hertz, and any value, whatever it is, the resistance remains the same. Okay. Then we can talk about the reactances and the impedance. The reactance and then the impedance on the y-axis as against the angular frequency. Again, we can also call it the normal frequency that we know of. Now, if we look at the capacitive reactance, it is the inverse. It depends on the inverse of the frequency. So if we have an inverse curve, it will look like this. So as the frequency increases, capacitive reactance reduces. The capacitive reactance, it decreases as the inverse of the angular frequency. On the other hand, the inductive reactance will always be linear. So the inductive reactance is equal to a certain value multiplied by the angular frequency. So this one, if this one represents x, then this one is going to represent the gradient. So it will be a linear relationship, which will move from 0 when the angular frequency is 0, and it will increase. So this one is for the inductive reactance. At any moment, these two reactances are opposite to each other. So if you want to find the impedance of these two reactants, then we'll always have to sum them or find a difference between each one of them. At this point, if we should find a difference, this one will almost be 0, so it will be the same value here. Then as we come, let me use a different color. Then as we drop down, we get to a certain point where they will have their minimum value, where the reactance will come down to 0. Remember, we can have the resistance here. This one should be the impedance, the total impedance. The impedance will vary, and at a point when the capacitive reactance and the inductive reactance are equal, they will have a total reactance of 0, and the impedance will be equal to the resistance itself. Look at this again. At a point when this one is equal to, when the capacitive reactance is equal to the inductive reactance, this sum here will be 0, and the square of it will be 0. So it will be r squared and then square root of this r squared, which will give us the impedance being equal to the resistance. At this condition, we say the oscillator, the capacitor, the combination of the capacitor and the inductor, which is oscillating current between them, is resonating with the source supply. So when we have the impedance being equal to the resistance, we see the oscillator, which is the combination of a capacitor and an inductor, are now resonating. It is now resonating with the source supply. Let me talk much further about this resonance. Remember, left with the capacitor and the inductor alone, they will be pushing current between them. We studied that in the previous video. So they will be pushing current between them. They'll be pushing current between them and energy in between them. Then this one will also be driving another current through the whole system. So the frequency with which this one, the oscillator drives current, is given by the omega LC. We saw that in our handouts. Let me go back to it. Okay, so this is the natural frequency of the capacitor and inductor combination. So the natural frequency of the oscillator, the LC oscillator, will have a natural frequency of the inverse of the square root of the inductance multiplied by the capacitance. So this one will give you the natural frequency of the oscillator. That means the oscillator itself is pushing current back and forth between the capacitor and the inductor. So this back and forth pushing of current has a certain frequency and it does not change so long as you keep the capacitance and the inductance constant. It does not change. Alright. Then the source itself will also be driving current through the whole system at a given frequency. So at resonance, the frequency of the source itself, which is this value, will be equal to the natural frequency of the oscillator. So when this condition is met, then we say the oscillator is resonating with the source. The source is also alternating. So if the alternating of the source is the same as the oscillation of the current between the capacitor and the inductor, then we say they are resonating. So these are the conditions for resonance. Let's go back to the main page and then recap all the features of resonance. So if we come to page 23, we have resonance. It says, notice that the reactance of the reactive component depend on the frequency of the AC source. Resonance of an RLC circuit is characterized by the following. The first point is that the frequency of the AC source is equal to the natural frequency of the LC circuit. That's what I've said. So the angular frequency of the AC source is equal to the natural frequency of the capacitor inductor combination. So this is one condition for resonance. When we have resonance, this is what you are going to see. The second point, the reactants are equal in magnitude. So the two reactances are equal in magnitude, and because they are opposite to each other, they cancel each other and they appear to be a short circuit. So the reactance, there's zero reactance. They don't have any effect at all on the current being driven through it. And the impedance is simply the value of the resistance. So the impedance becomes the value of the, because the reactance is zero. Remember, the impedance is given by R squared plus, into brackets, inductive reactance minus the capacitive reactance, all squared. So if this is zero, then everything here will be zero, leaving the R squared. The square root of it gives you the impedance. Then the next thing is that the current is maximum. So if we have a current that is being affected less, then we have a maximum current that will be flowing through the whole circuit. So this one is pushing current back and forth. So if this one is pushing current back and forth with a different frequency, then there is going to be a moment where this one will be pushing current in this direction and this one will also be pushing current in the opposite direction. So if the frequencies do not agree, then they will reduce each other at some point. So if they are not agreeing to each other, then this one may reduce the current effect of the main source. All right. But if they are in agreement, when this one is pushing current in this direction, this one also be pushing current in this direction, then they will have maximum current flow. If they have the same frequency, this one pushes and this one pushes in this direction, then they will have maximum flow. But if they don't have the same frequency, this one pushes current in this direction, this one pushes current in the opposite direction, the effective current flowing through will reduce. So resonance is achieved when they have the same frequency. This is the natural frequency. This one doesn't change, so long as the capacitor and the inductor are the same. If we want to change the natural frequency, then we may have to vary the capacitor, either close it a bit or open it a bit, so that it will agree with the source frequency. This is how we use it to tune radios. We'll talk about it when we do electromagnetic. So the next point is that the voltage across the AC circuit is in phase with the current in the circuit. In other words, the phase difference between the voltage and the current is zero. So this is what we mean. If we draw a curve of the current and the voltage, then this is what will happen. They will be in phase. When the current gets to its maximum, the voltage also will be at its maximum. This is what we mean by they are in. Alright, then finally, the power in the whole circuit is maximum. There is maximum power dissipation. So the current will have the current through the circuit will be maximum. So the resistor can now heat up to its maximum. Unlike previously, when we didn't have resonance, the resistance will have less current, so less energy will be dissipated. So that is about resonance. For now, you can go through it again, and I believe, I trust you, you understand the whole concept.